Hello, this is Rob Froney, and I'm here to explain adaptive finite impulse response filters. Here we have an adaptive FIR filter. There's a regular FIR filter here with coefficients W sub n of k. There are capital N of them and coefficients down here. And you convolve the input to that filter, x of n, with the W sub n, and you get the output here, d of n hat. We have a desired output, d of n here, and if you notice this is looking like a feedback and control system. D of n and minus d of n hat gives us the error signal, e of n. That error signal is fed into an update algorithm along with the input, and that information is used to compute an update to the coefficients, a new change to the coefficients delta w sub n, so that the coefficients delta w sub n of k will add on to w sub n to give us the next coefficients, w sub n plus 1. Down here we've got to figure out how to do this update algorithm. What are we going to do for that? So I suggest the thing we want to do is we want to minimize the error here in some way. Actually not minimizing the error, otherwise it would go to minus infinity. We want to bring it as close to 0 as possible. That would mean we could minimize e squared of n. So let's minimize e squared of n. That would, when you do that, that will bring e as close to 0 as we can get it. Now the error of n, you can see up here, is just d of n minus d hat of n. And let's draw a little picture down here. If we look at this little thing, we've got a picture here for the case n equals 2. We've got the w sub n of 0 axis and the w sub n of 1 axis, and those things, you know, have an influence on this this d sub n up here. Let's look and see what would happen if we were suppose we were right here on that contour line of e squared. And down here, suppose this point right here was the minimum. So this is like a big hole. We'd like to kind of get down in that hole. So I'd like to take a step from where I am right here toward that hole. That means in the down direction. And if you notice, there's, you know, I could take a big step, but if I take too big a step, I might end up bouncing around here and not converging. So if I take a small step toward that hole, I would move in the direction perpendicular to the contour line, which is in the direction of minus the gradient of this function e squared. And so if you notice, basically what we're going to do is we're going to move in the w0 direction a little bit, you know, like this. Move it like this in the w0 direction. In the w1 direction we'll move it like that, and we'll in effect get this vector right here, headed for that guy, hopefully. So how do we write that mathematically? Well, what we'd say is delta w sub n of k is equal to negative. I want minus the gradient because I want to go toward the minimum. So I put a negative sign here, and then I put a thing mu, that's my step size. And then I want to take a derivative of the function e squared of n with respect to w sub n of k. So the derivative in the 0 direction, w sub n of 0, would be this little vector here. And the derivative in the other direction would be that little distance right there, and so you add those two vectorially, and you get this gradient vector here, which gives us the two components of delta w up here we want to minimize. So the next thing we got to do is we got to figure out how to take the derivative of e squared. So that's not too hard. Taking the derivative of e squared using chain rule is 2 times e times the partial of e with respect to w sub n of k. We're basically using the chain rule here. Now e is equal to d minus d hat of n. We got to still figure out this partial of e with respect to w sub n of k, and if you take the partial of this guy with respect to w sub n of k, d doesn't depend on w sub n of k, only d hat. So it would be minus the derivative of d hat with respect to w sub n of k would be this term right here. So d hat is the convolution here of w sub n with x sub n. This is the definition of convolution here. And if I take the derivative of that guy with respect to Wn of 1, I only get x of n minus 1. And if I do it with respect to Wn of k, I get x of n minus k. Only one term. All the other w's, derivative of w1 with respect to w2 is 0. So the derivative of d hat with respect to w sub n of k is x of n minus k. So then the derivative of minus d hat is minus x of n minus k, and I'm going to plug that minus in there, which will cancel out that thing, so I get w sub n minus k equals 2 mu e of n x of n minus k. So now we have a formula for the change in w sub n up here as a function of what's coming in. The x of n minus k comes in right there, and the e of n comes in there, and you just plug them into your formula, and you got your w sub n, and you add that on, or your delta w sub n, you add that on to w sub n, and you got the w for the next time around. So this has been an explanation of adaptive FIR filters. Hopefully this helps you understand them.